So let's return in our minds to the late 1980s, the discovery of the cosmic microwave background, the calculations of Big Bang nucleosynthesis had by then pretty much dispelled doubts over whether the Big Bang was real or whether these calculations made sense. The idea that we would actually one day be able to make measurements in detail of the parameters of this isotropic homogeneous universe seemed at the time to be a little bit far-fetched, and so what cosmologists did is they played around with models based mostly on their theoretical or aesthetic preferences. The 1990s ushered in what is now known as the era of precision cosmology, that surprised many of us in turning cosmology from this sort of speculative field into a field in which research is based on hard evidence. And the first of these precision results was the measurement by the COBE satellite in the early 1990s of the inhomogeneities in the cosmic microwave background. Remember, the cosmic microwave background is completely homogeneous to within a few parts in 100,000, but then when precision measurement to that accuracy became available, and the COBE satellite and the Boomerang balloon project were the first to make these measurements, then the first thing to be discovered, we recall, was the dipole moment reflecting the Earth's motion through the cosmic microwave background relative to the local Hubble flow. And then when one subtracts or takes into account the Earth's motion, we see that in this COBE map of the sky, we see that even taking into account Earth's motion, we do not have a completely homogeneous sky. The plane of the galaxy here is hard to measure, but to within 1 part in 10,000, there are hotter regions here in blue and cooler regions here in red. And the COBE satellite produced the first image. It was clear that this is a very important result. Remember, these are inhomogeneities in the sky that we see back at the time that the universe was 380,000 years old. This is the oldest vestige of structure in the universe. Note that as soon as we admit this, we are moving outside our comfort range. We are no longer dealing with absolutely homogeneous isotropic cosmology. We are encountering the first signs of inhomogeneity. Well, this is good. The universe as it is now is certainly not homogeneous. There are galaxies and clusters, planets and me. And so somewhere this had to have developed. These presumably are the seeds of what we now find as the intricate structures of clusters and superclusters and giant voids in today's universe. Measuring this with high precision was obviously of high importance, and so the Wilkinson microwave anisotropy probe in 2003 produced this map. Again, Earth's motion has been subtracted. You see that the resolution is much higher, and about a decade later, in 2013, the Planck satellite produced the highest resolution map ever. You notice that here the galactic plane is not obscured. The truth is that it's still hard to measure exactly in the plane of the galaxy because there are too many other sources. The galactic plane has here been sort of added in statistically. But be that as it may, we have here a picture of the sky as it was at the time the universe was 380,000 years old. There is clearly some information here. What is it that we learn? Well, the dark and light areas, or the hot and warmer regions, seem to be scattered, and indeed are, somewhat at random throughout the sky. We will discuss exactly this randomness as we go on, but there is no real pattern in this data. However, so that the methods that one needs to use to address it are statistical. And the first and most significant, if you will, statistical measure applied to this data is what we call the two-point correlation. This is the object we discussed in the past when we discussed the density of galaxies in the universe. We said that the average density of galaxies was roughly homogeneous. But there was this two-point correlation function which basically told you as a function of distance, if I find a galaxy here, what do I learn about the probability, how different than the average is now the probability of finding a galaxy at a distance d from that first one as a function of d, and we saw that there were correlations, there was a non-zero impact. Finding a galaxy did make it more likely to find another galaxy, because galaxies typically cluster, and then this sort of peaked at a distance of about 100 or 150 megaparsec, and beyond that there was no structure. Beyond that there was homogeneity. Knowing there was a galaxy here told you nothing about what lay 300 megaparsec away. And so we can make the same kind of analysis to the microwave sky, and what we're looking at here is the two-point function on an angular scale. So what we're asking is, if I know that there is, say, a warm spot in the microwave background here, at an angular distance of 1 degree, 2 degrees, an eighth of a degree, depending what you want, what does this tell me about the likelihood of finding a warm spot this angular distance away? And it's clear that there is some structure here. At distances larger than a couple of degrees, you learn pretty much nothing. There are no correlations. As we will see, this totally makes sense. There is a very significant and obvious peak at about 1 degree. If you know that there is a warm spot here, there is very likely to be another warm spot about a degree away. And similarly, a cool spot. And then there are secondary peaks at higher, smaller angles. And the structure of all of this, this is WMAP data. There have since been improvements through the Planck satellite, which carried more precise measurements off into small angles. You saw that we got a higher resolution image of the sky. For our purposes, this is quite sufficient. And this peak at about 1 degree is very meaningful. What is this? Well, you would expect in this early dense universe, remember that we are seeing the temperature of the photons emitted at the surface of last scattering at the time that light decoupled from matter, roughly the time that hydrogen and ions combined to form neutral hydrogen atoms, and the universe became transparent. Now, just before that, we had this dense hot plasma in which baryonic matter and light were strongly coupled. And if there's any inhomogeneity, which thermal fluctuations, if nothing else, should have generated, though we'll have to go back and see where they came from, any inhomogeneity in this plasma, well, you can imagine there's a region that's a little bit denser. And if it's a little bit denser, it gets a little bit hotter. And if it's a little, because of the ideal gas law, and if it's a little bit hotter, then radiation pressure, the local higher temperature generates higher radiation pressure, trying to make the region expand. This expansion causes the region to rarefy, compressing nearby regions. What you get is essentially a sound wave in this plasma, an oscillatory behavior where a region of compression periodically compresses and rarefies, and this propagates through this plasma at the speed of sound in plasma. And so what we are seeing in some sense is the images of these primordial waves. Great. Now, there's a bit of a comment that I need to make because it's confusing, but is that it turns out you would expect that at some point what's going on is this plasma is oscillating in various ways, and it's got various sound waves running through it, and then at some point temperatures cool down, hydrogen atoms recombine, and whatever light was propagating at that time just keeps going. So we get basically a freeze frame of this oscillating behavior. And you'd expect that the regions that were hotter are the regions that appear hotter in the microwave sky. Turns out this is not quite correct because of something called the Sachs-Wolf effect. It is true that regions that are denser were warmer and emitted a higher temperature microwave background, but regions that were denser are also deeper gravitational wells. And so light leaving those deeper gravitational wells is redshifted. This turns out to overwhelm the effect of the thermodynamic heat of these regions. And so, in fact, the warmer regions in the microwave sky are regions of lower density, and the highest density regions appear as the coolest spots in the microwave sky. Be that as it may, what we've discovered is that we can see in the sky an image of this primordial propagating density wave. Now, point is that we have a guess for the wavelength of this primordial sound wave. We'll get into a little more of the details later, but here's a way to estimate the order of magnitude. See, we have this sound wave, and we want to estimate the size of a region that can in some coherent way compress. And we have a lot of experience with doing this by now. The size of a region that can coherently compress has to do with the size of a region that can communicate from this side to this side and sort of all compress together, or all dilate, rarefy together. And so typically we would have said this region is limited by the horizon distance. Now, the horizon distance is because we imagine that the fastest that information can be communicated from one side to the other is the speed of light. In the current case, the relevant way that the signal density patterns propagate is the speed of sound. And so what we expect is that the wavelength, the largest wavelength of the fluctuations we are likely to find in the microwave sky is going to be the distance that sound can travel in the plasma in the 380,000 years that the universe had existed. So how far is that? Well, the speed of sound in plasma, because of this strong coupling between charge and radiation, turns out to be very high. There's this very strong restoring force associated to charge separation. So sound travels through this plasma at 1 over square root of 3 approximately times the speed of light. And so you can ask, how far has a sound wave moving this fast traveled in since the time say of the beginning of the dust-dominated era? The properties of the radiation-dominated era are a little bit different, but remember that was a small perturbation at the beginning. And we know this. We know that the distance that light could have traveled by this time is what we call the horizon distance. So we expect sound waves with a maximum wavelength, which is 1 over square root of 3 for the rate of the change in the speeds, times the horizon distance. And the horizon distance in the dust-dominated era, as we've described before, is basically 3 ct. So dividing by the square root of 3, we get root 3 c times the time of ionization. Remember, that's 380,000 years. And now, therefore, we know this wavelength. In today's units, that's about 200 kiloparsecs at the time. Now, we are looking at this wave. Remember, we're measuring angular distances. Oh, we know how to do that. We need to know the coordinate distance to this object. Well, the coordinate distance is the distance that a photon will have traveled from this time, T ionization, the time when the universe became transparent, the time of last scattering, and the present, T0, and the distance that a photon propagates in a dust-dominated universe, which describes rather accurately our universe, is given by this expression. Deriving it requires an integral, so we're not going to do it, but you can at least note that if I set T to 0, T ionization to 0, so this is the distance that a photon travels from the time if it was emitted at T ion and observed at T0, you notice that a photon emitted at T ion equals 0 at the Big Bang would have traveled 3 ct, which is what I claim to be the horizon distance. And so during the dust-dominated era, we know that A of T is A0 times T over T0 to the 2/3. A0 is 1. I can write A of T like this, and I see that this ratio is the scale factor at ionization to the power 1/2. So I have this expression in terms of the scale factor at ionization to the 1/2. Note that I'm pretty sure I know the scale factor at ionization to the 1/2 because the temperature at ionization is the current temperature of the cosmic microwave background times A at time of ionization inverse, and we said this is about 3,000 Kelvin, so we know that ionization is about 1 over 1100. And so we know this coordinate distance, we know this wavelength. We are all set up to do a small angle calculation. So let's do the small angle calculation. I'm going to make some assumptions to simplify life. I'm going to assume a flat universe, so I can use Euclidean geometry. And I can use the small angle formula. Remember, I computed the coordinate distance. I have to remember to convert it to an angular distance because I have to take into account the expansion of the universe. And so I expect that the angle corresponding to one wavelength of this primordial sound wave at this distance will be 206,265 arc seconds, or 57.3 degrees, times the wavelength divided by the angular distance. The angular distance is what the coordinate distance divided by 1 plus z. 1 plus z is 1 over a. So I plug in, this is lambda. I plug in for 1 plus z is A inverse. And the coordinate distance, I plug in what we computed before. And now I can simplify this expression. I see that root 3 over 3 leaves me with a root 3 on the bottom. The c's cancel. T ionization divided by T0, I write as T ionization divided by T0, as we know, is A ionization to the 3 halves. And so I multiply A ionization to the 3 halves by A ionization inverse, and I get A ionization to the 1 half, and this is my expression. Remember, I know what A ionization is. It's about A ionization inverse is about 1100. I plug in the numbers, and I predict an angular size for my acoustic features in the microwave background of about a degree. This is almost precisely what we found. So what have I actually demonstrated here? Well, I claim that what I demonstrated is the correctness of my assumption that the universe is flat, at least to a very high precision, precisely flat. How have I done this? Well, remember, I used the small angle approximation to relate this angle to this properties of this triangle. The small angle approximation is based on Euclidean geometry. If the curvature of space were negative and triangles looked like this because geodesics diverged, I would have expected to measure an angle smaller than what the distances suggest because geodesics diverge, whereas if the curvature of space were positive, I would have expected to measure a larger angle. The fact that I get exactly the angle measured tells me that the universe is flat. Now, does this tell me that k is 0? Well, what it really does is it puts a limit on that parameter r0. Remember that the divergence from some of the angles being 180 degrees in a triangle is proportional to its area divided by this parameter r0, or multiplying this parameter r0 with units of inverse area. We have here a triangle with a rather significant area. Remember that this side is about 46 billion light years. And so we have a huge triangle satisfying the axioms of Euclidean geometry. We have a very stringent restriction on the curvature of space. This justifies my assertion early last week that we actually know space is flat. Here is a graphic demonstration of this. You measure a triangle. If the curvature of space were negative, if space were hyperbolic, you'd observe a smaller angle. And the fact that we measure 1 degree, that our calculations agree with the measurement, tells us that to very high precision over this huge size that we are measuring, the universe is almost precisely flat. An amazing, startling result. There is lots more information in the further structure of the inhomogeneities in the microwave background. We will return to some of it. Notice now we understand why basically the correlation drops to 0 at larger distances. Regions that were separated by more than the horizon distance had no way to communicate since the beginning of the universe, and so a hotter spot here should not give you any information about the temperature there at distances that had not communicated by that time in the history of the universe. So this vanishing is very meaningful. The structure at small angles turns out that it describes, turns out to be providing us far more details, and we'll come back to it, about the relative density of baryons and dark matter. And when we look at the structure of these sound waves in the next clip, that should become more clear. We have learned a lot from the microwave background, and we are still in the process of analyzing polarization data and so on from the Planck satellite, and we should be learning a whole lot more.